Hello, Mrs. Below here. In this video I'm going to be going over the mole, not this type of mole, but a unit that we use in chemistry. So what is a mole? So chemistry is a quantitative science, meaning we often have to be able to count things and measure things. So therefore we're talking about really small things, so we need some type of a counting unit. We need a unit to count things for stuff like atoms, which are really, really small. So we use moles to measure small things like atoms or molecules. This number right here, this is called Avogadro's number, and it is found on the back of your periodic table. This is very similar to 12 eggs means like a dozen. Okay, most people don't say, oh, I have 12 eggs. They say, oh, I have a dozen eggs. And it's kind of the same thing here. Instead of saying I have this many atoms or molecules, which this number, this isn't scientific notation, this is a huge number. This would be 6.022. It's times 10 to the 23rd, so I'd have to move it 1, 2, 3. I'd have to move it 20 more spaces to the right here. Yeah, so that's a lot of zeros. That's 20 zeros, okay? That is a huge number, okay? So instead of saying I have that huge number of atoms or molecules, I could just say I have 1 mole of whatever substance it is you're talking about. The atomic weights on the periodic table, those decimal numbers, so for example, hydrogen is 1.008. That also, it's not only the average atomic weight of all the isotopes for that element, it is also the molar mass, okay? So I'm actually going to use carbon as an example. So carbon has a molar mass of 12.011. So if you have 1 mole of carbon, that's the same as saying you have 12 grams of carbon, and you would actually know exactly how many atoms of carbon you had. So imagine that you had 12 grams of carbon, like you took pure carbon, you put it on a scale, you weighed it, and it weighed 12 grams. You would have 1 mole of carbon, and you would actually know exactly how many atoms of carbon you have as well, which is kind of neat because counting atoms, right, they're so small, it could be really difficult, but this is one way that we can count them. So molar mass, as I mentioned, is the mass of 1 mole of a substance, and all elements have their own unique molar mass, right? On the periodic table here, all of these decimal numbers are unique for that element. And the units that we use to represent molar mass is grams per mole or gram/mole, okay? So for example, hydrogen, if we look on the periodic table, is 1.008. We could say, and again, if we're just talking about like hydrogen, we're just talking about 1H, this many grams per mole. Okay, we could write it like that. Or you could also write it as 1.008 grams equals 1 mole. Again, this is really important for when we get to picket fences. Also, you could say that this is equal to 6.022 times 10 to the 23rd atoms of hydrogen. Okay, so all of these are equivalent to each other. So if you had a gram of hydrogen, you would have about, if you had about a gram of hydrogen, a little over a gram, you could also say you have 1 mole of hydrogen, and you would know exactly how many atoms of hydrogen are present without having to count them. So again, every element on the periodic table has its own unique molar mass. So nitrogen is 14.007. I'm sorry, nitrogen is, 14.007. Oxygen is 15.999. For this class, I'm fine if you just say 16. That's acceptable. Okay, if we're just talking about nitrogen and if we're just talking about oxygen. Okay. So that's pretty straightforward. If you want to know the molar mass of a particular element, you just have to look on the periodic table. However, we don't always have just like pure forms of elements. Oftentimes we have elements, multiples of elements, or different elements bonded together. So how do we figure out the molar mass of something like a compound or molecule that has multiple elements and maybe multiples of the same element? Okay, here's how we're going to do it. Okay. So hydrogen and oxygen, that makes up water, okay, H2O. So you're going to start with the molar mass of each individual element. So I'm going to start with hydrogen. As we just said, hydrogen on our periodic table is 1.008. So I have the molar mass of just one hydrogen. However, according to this, there are two hydrogens, okay, H2, okay? So I have to take the molar mass of hydrogen and I'm going to multiply it by 2, okay, because you have two of them. Versus up here, this is this, if I was just talking about that one individual element. But we also have oxygen. So what we're going to do is we're going to add the oxygen. Now, in this situation, I just have one oxygen. Remember, oxygen, we're just going to say is 16 plus 16, okay? Because I just have one oxygen. So I'm going to go ahead and put that into my calculator. 1.008 times 2 plus 16, 18.016. And again, this is molar mass, so the units that you can use are grams per mole. So if I actually weighed out 18 grams of water, which is the same as saying 18 milliliters of water, because the molar mass of water is 1 gram per milliliter. If you had a graduated cylinder and you filled it up with 18 milliliters of water, and actually if you weighed it, it would be 18 grams of water, you would actually know how many molecules of water are in that, because this is the molar mass of that. Again, you can say 18.016 grams is equal to 1 mole, and this is also equal to Avogadro's number, which tells us how many molecules or atoms would be present. Okay. All right, so that's water. Let's do another example. Please note that this should be a lowercase l. This should also be a lowercase e, because on the periodic table, that second letter, if you have 2 letters in the chemical symbol, it always should be lowercase. So next we have chlorine, which is Cl2. So this time we only have one element, chlorine, which is right here. And its molar mass is 35.45. So I have 35.45, okay? And again, with just one element here, chlorine, there's a 2 here, so I am going to have to multiply this by 2. 35.45 times 2, 70.9, and again we can say grams per mole for our units. All right, let's do another one that's a little bit more challenging. So we have FeOH2. This would be iron 2 hydroxide for its name. So again, we're going to do each element individually, and then we're going to have to do some multiplication with some of those. So I'm going to start with iron, which is Fe. So there's only one iron, okay? If I look at my periodic table, 55.845. Okay, Now there's only one iron here, so I don't have to, there's only one iron here, so I don't have to multiply it by anything. It's just one iron. Okay. Plus, all right, so here is the part where it gets tricky. So I have this, and then I have this on the outside, okay? So you can think of this notation. So again, there's two elements inside of parentheses, and then there's a number on the outside. So this is literally saying that you have two OHs, okay? It's called hydroxide, okay? So you have two oxygens. Remember, oxygen is 16, and I would multiply that by 2. Hydrogens, you also have 2 of them. So again, here's hydrogen. We would multiply that by 2. Do our math. So 55.845 plus that's 32. That's 1.008 times 2. So 89.861 grams per mole. Okay. All right. So what happens if we have this situation here, but for something a little bit more, like there's a little bit more going on here. So I'm going to go to the homework, which is in the molar mass worksheet here. Okay. I'm going to go over number 1, okay, because this has a lot going on with it, okay? So this right here, I want to talk about this, okay? I'm not going to get into the aluminum, but I want to focus on this piece here. So you have SO3 on the inside, and then there's a 3 on the outside here, okay? So again, this is literally saying that you have 3 SO3s, okay? So you would have 3 sulfurs in total. However, you would have 3, 6, 9 oxygens in total. So you can look at it this way, or you can look at it as if you're distributing this number to everything that is inside of the parentheses. 3 times 1 sulfur is 3. 3 times 3 oxygens, that is 9. So in this situation, you would have 3 of the sulfurs, and you would have 9 of the oxygens.